and my presentation will be all about technical stuff. So Accenture is not just a management consultancy, contrary to what you might have heard about it or think about it. There are also people there doing deeply technical stuff. The part of Accenture that I work for is called Accenture Mobility. We're interested in all aspects of embedded and mobile devices, in providing software for those devices. We do work on lots of different platforms. The usual suspects are listed up there. And we do all kinds of work, from app development work through device engineering, device and platform engineering, which is where I fit in, through to delivering end-to-end solutions, back-end servers, that kind of thing. And we work in all kinds of industry sectors. And as it says there at the bottom, the lucky few of us in Accenture Mobility get to work on Qt, which is what I do on my day job. So a little bit about me. I live, work, and play in London in the UK. I've been working in embedded software for about 6 years, most of that time for my sins on Symbian. So I worked for a while on developing the lower parts of multimedia adaptation stacks for various Symbian devices. Lately, been working in a bit more in the graphics area. And for the last 2 years, I've been part of the team that's been porting Qt to Symbian. And so there, I've been mostly focusing on multimedia. So developed a phone on back end, and more recently, some other back end for QtMultimediaKit. OK, so before I get onto the content of the presentation, I just wanted to mention a few conventions that I'll use. So I'll show a few demos during the presentation. Unlike some of the other speakers, I'm not brave enough to do live coding. So I'm going to show you a few demos. For a frisson of excitement, I will use 2 different mobile devices, so there is at least some risk something will go wrong. But it's all pre-coded, and the code for almost all of the demos I'll show is available via this Gitorious repository. And so when I show a demo, I'll put the path within that repository in a blue box, so you can find the code later on and play with it. Most of this presentation applies to all mobile platforms targeted by QtMultimediaKit, but there are some bits which are specific, and so I'll label those with an appropriate symbol. OK, so this is what I'm going to cover in the next 45 minutes or so. QtMultimediaKit, as you'll have heard if you went to Jonas's great talk in the previous session, provides you with a set of cross-platform abstractions for doing a range of multimedia use cases, multimedia rendering and multimedia capture. So because those are cross-platform, why do you need to care if you're targeting a mobile device? What's the purpose of this session? Well, no abstraction is perfect, and there are some constraints and some particular characteristics of mobile devices which mean that you might need to tune your application slightly to work better on those devices. So I'm not going to talk about creating layouts for small screens and things like that, but there are some multimedia-specific things that you might need to be aware of. So how best can you get your multimedia applications to really sing on a mobile device? OK, so as a little lead into that, I just wanted to look at a few areas in which mobile devices are different to the desktop targets you might be more familiar with. So hopefully none of this is new to you. But mobile devices tend to have less processing power. The gap is narrowing, but they are still slower CPUs than desktop devices. And also, partly as a corollary of that, there's a reliance on co-processors. So whereas a lot of work may be done on the CPU on a desktop machine, in multimedia, it tends to be deferred to co-processors on a mobile device. And that can have some impact on the runtime characteristics. Mobile devices are richly connected, and they tend to have lots of different ways in which they can connect to the network. So when you want to do multimedia streaming, there are different routes that the data can reach your device. So you may need to think about that. And they tend to have limited memory. So as with processing power, multimedia use cases can be very hungry on memory as a resource. So some careful resource management may be necessary. So looking at those considerations, what might you need to think about when you write your applications? Well, the lack of processing power and reliance on co-processors may lead to higher latency. It takes longer for things to happen on a mobile device. So when you want snappy response, you need to make some small changes, which I'll talk about in your application to achieve that. In terms of connectivity, you may need to have, or you may want to have programmatic control over which access points your application is using to stream data from the network. And in terms of memory, as I mentioned, you probably want to monitor and possibly manage the amount of memory that your application is using. And the other thing which you may want to think about with mobile devices is they're great platforms for cool demos. So they're always in your pocket. You can show the demos to your mates down the pub. So they're a really good way of showing off some very cool capabilities of Qt and QtMultimediaKit, which I hope to demonstrate. OK, so the first of those topics then, low latency and how to achieve it. So as hopefully most people in the audience know, there are a couple of sources of latency. So when you apply some user input to your device, the amount of time it takes then for a response in terms of video being shown on the screen or sound coming out of the speakers is the consequence of two things mostly. So resource allocation, so starting up co-processors, configuring hardware, allocating memory, and then filling that memory with some data which is ready to be played. And then it'll hit the rendering output. So when you're looking at a media playback use case, so browsing through your playlists and pressing a button to start the song, both of those two things are likely to be a consideration in terms of how long it takes for that song to start. If, on the other hand, you're writing something like a synthesizer application or a game which requires a very fast response, likely you can pre-allocate the resources, but you may need to actually fill the buffer in real time. So the amount of buffering time is going to be a consideration. So QtMultimediaKit provides some APIs for you as an application programmer to have some control over those things, which is shown here. So there are a series of states which the QMedia player C++ object or the audio and video QML objects transition through as they start playing. And those are listed there from no media through to buffered. And once the data is buffered, it'll start playing. Now, the triggers to transition between those states are shown there at the bottom. So setting a source in QML or calling set media on a QMedia player will trigger a transition from no media to loading and then through to loaded, assuming there's no problems on the way. And then once the clip is loaded, calling play, either in QML or in C++, will cause the data to start buffering and then playing back. So as I said before, if possible, if your application logic allows it, you can reduce the startup latency by preloading audio sources, so by doing that first yellow block of latency ahead of time. The amount of time it takes to buffer data is not controllable via the high-level APIs in QtMultimediaKit, but I'll speak a little bit later about the lower-level audio output APIs. OK, so straight onto a demo. So this is a QML application, a fairly simple one, which is running on a Symbian device, but it also runs on Harmattan. And so what we've got here is two audio elements in QML, shown in those top and bottom bars there, and then some buttons to start and stop media playback. So if we just look at the top one there, test1.mp3, if I just hit play, then hopefully the sound will come out of the speakers. I don't know how loud it's going to be. Quite loud. I can turn it down here. Oops, that was interesting. OK, so hopefully you noticed that when I hit play, there was a short delay there, and you might have seen the states transitioning through on the right-hand side from no media through buffered to playing. I'll just do that again. Oops. So it's not a long time. You're not going to go and make a cup of tea, but it's a noticeable delay. If, on the other hand, you click load, so that causes the QML application to call source equals test1.mp3. You can see now we're transitioning to the loaded state, and then when I hit play, oops, it's a more immediate response. So the amount of difference that is going to make will differ from device to device, but certainly on the Symbian devices that we've been playing with, it is noticeable. So it's just really a tip to think about. And the other thing that I should mention here is that, again, this differs from device to device. On this device, we can load up the second clip while the first one is playing, and therefore your application logic can create gapless playlists. So if you have your first one playing, you can load the second one. You can actually play them. Well, OK, that doesn't sound very good. It's kind of the same clip mixed with itself. But if you had a real application, as the first clip reached towards the end of the playback, you could load up the second one and then have it ready to go to minimize the gap. So take a look at the source code. As I say, the application is there on Gitorious. OK, so the other angle on latency is using the low-level audio APIs. So in C++ land, there are the following APIs, QAudio input and QAudio output. And they are paired with QIO device. So the way that you use these APIs is to use a QIO device to either provide data to the output or read data from the input. And so I'm going to talk about now how you can use these APIs to best effect and to get the lowest latency response possible. So if you've looked at these APIs, you will know already there are two overloads of the start function in QAudioOutput. One which tends to be called push, which provides you with a QIO device, which you then write data into. And the other one, which tends to be called pull, where you provide your own QIO device subclass, and then the QAudioOutput will pull data from that as it becomes available. So there's some trade-offs between those two, both in terms of their ease of use and the runtime characteristics. The one which provides you with a QIO device, the push overload, is easy to use because you don't have to write your own QIO device subclass, but it requires an extra buffer copy from the client application into the audio stack, at least on Symbian. The pull overload, on the other hand, doesn't. It allows you to write directly into the buffers which are made available by the native audio stack. So it's a better choice for low latency processing, but it does require you to write your own QIO device. Whichever one you use, there is an API called setBufferSize, which allows you to, well, do what it says in the tin, control the length of the buffer. This API, unfortunately, is not supported on Symbian. So whereas you might think you could call that to allocate a shorter buffer size, don't allocate it too short or you'll get underflow errors, but reduce it slightly in order to get a lower latency response. It actually won't do anything on Symbian. So the buffer size you get on Symbian is always 4K, and therefore that can be up to a quarter of a second, depending on the sample rate of your data. But what you can do instead is you can throttle the amount of data that you provide to QAudioOutput via the QIO device. So if you write your own QIO device subclass, you'll have to implement a function called bytesAvailable, which the QAudioOutput will call in order to find out how much data is available for playing. And if you just provide the data to the QAudioOutput in small bursts, then you'll get a lower latency response from it. So I'll try and demonstrate that with this application. You can probably guess what it does. So this is a QML C++ hybrid application. The reason being that we're using the QAudioOutput API, so we need to use some C++ to interact with that, whereas the UI is written in QML. So if I just play this as it comes out of the box, there's a fair gap between the impulse and the sound coming out of the speakers. And there's also data which gets left over in the buffer. So we get this sort of nasty transition from one note to the other. However, if we just bring up this menu and just reduce, so you can see there that the buffer size was a quarter of a second, so 4K at 8 kilohertz. If we just reduce that down to 32 milliseconds, then we get a much nicer response. Okay, I play the guitar, I don't play the piano, so I can't do anything fancy. But as I said, if you reduce it too much, you're going to get underflows and nasty effects. Okay, actually, we seem to be getting away with it at 16, I suspect. Ooh. Wow. Okay, we got there in the end. So yeah, there's a bit of tuning to be done. Again, it's going to vary from device to device, but the point is that on most platforms, you can use the setBufferSize function. On Symbian, for limitations of the native multimedia stack, that isn't implemented, it doesn't work. So therefore, you have to throttle the data at the QIO device stage. Again, look at the source of the application for more details. OK, so on to the next topic. Apologies, I'm going through this fairly quick, but as I say, this is all available, the source code afterwards, and you can ping me with questions later. So network streaming. As I mentioned, there are many different ways to get data off various networks onto the device for playback, and so this is going to talk about how you control which access point your application wants to use. So, but before I get onto that, I just want to just quickly go over the APIs which are available for streaming playback in QtMultimediaKit. So QMediaPlayer is a wrapper which sits on top of the native multimedia stack of your platform. And it has an API that allows you to provide a Q URL. So that's the easiest way to play data from a network source. However, depending on your application, you may have some requirements which mean that isn't the most suitable route. So for example, let's say that your application has some sort of custom DRM schema. So you're getting data from some source which has an encryption which is not natively supported on the platform. So your end-to-end service, your server and your device application share some DRM protocol which is custom to your app. In that case, you'll need to use a different route to get the data into the native multimedia stack. Or if you're using some kind of custom network streaming protocol, the same thing will apply. So in that case, you'll need to use the QNetwork APIs to create a socket of some kind, suck data out of that socket, and then provide it to QtMultimediaKit for playback. So there's an API to do that. This is starting to sound a little bit repetitive, but this is not supported on Symbian. Again, for limitations in the native multimedia stack, other platforms do provide some support for this. So there's an API which, instead of passing a URL, you can pass a QIO device which contains your compressed data inside whatever container format you're getting it from the network. On the other hand, if you want a combination of using some kind of custom DRM schema or custom protocol, and you also want low latency output, maybe you want to feed that data from the QIO device into QAudio output. So as I've mentioned before, there is an API that allows you to connect a QIO device up to QAudio output, so it looks like we're good. The problem here that I should point out is that although the QAudio output API has the capability, or offers the capability to query formats and set different codecs for the format of the data that you want to play, in actual fact, on all platforms today, only PCM data is supported via QAudio output. So in that case, if you want to use that route, you're going to have some kind of decoding happening in your application to transform your audio data into PCM before you give it to the QIO device. Sorry, the QAudio output. OK, so that was just a quick roundup of the different APIs which are available for streaming playback. But let's assume that we're looking at the fairly easy case where you've got a QURL that you're passing to a QMedia player, and what you want to do is control which network access point gets used. So by default, again, this will vary from platform to platform, but on Symbian, for example, if you haven't set a preferred access point, then when you start playback, the system, the platform will pop up a dialog asking you to select whether you want to use your 3G connection or wireless or whatever other access points you've got set up. But you may want to have more control than that. So either you want to just simplify the user experience, so you don't want to have dialogues popping up, you just want the stream to play. Or maybe there's a reason where the needs of your application mean you have to use a particular network. So you might work for a company which is developing some kind of video chat application, video telephony, and maybe the latency that you get over a cellular network is too much, so you want to just make sure you always use a Wi-Fi network. In that case, your application may want to select the access point programmatically rather than letting the user select it. And to do that, there are a few APIs available. So the first API listed there is in the QtMobility Bearer component module. And that allows you to ask which network configurations are available. So that will give you a list of all the different access points which are available to you. And each of those has associated with it various information, such as whether it's actually available now, or whether it's configured but not available at this time. So you've got an access point, a Wi-Fi point set up, but the router's out of range or something. So your application can then select one or more of those network configurations and tell QMedia Player, use these network configurations in order of preference. So that's the second API there, set network configurations. And then there's an API which allows you to query from QMedia Player which network configuration it's currently using. So that might be useful for providing feedback to the user. There are no QML bindings for these APIs at present, so this, again, is all in C++ land. OK, so we've got another demo here. I'll just quickly talk through this slide before I go to the phone. So it's a hybrid QML C++ application. It's called Network Player. And what it does is provides you with a list of the currently available QNetwork configurations, which they've got 4 of them shown there, and their associated state. So whether or not they're active or discovered, defined, undefined. And so the application then allows you to, it's got a URL hard-coded into it, which it's actually a video URL, but we're just going to play the audio stream because I wanted to keep the UI simple. And when that URL starts to be played, we'll see the status change in that status bar, second from the bottom. And then when we actually connect to a network, the application will report which network configuration we're currently using. Alternatively, the user can actually select from that list at the top. So that sort of demonstrates the set network configurations API. So let's see if we can get this to work. I'm just going to set up, I've got an access point on my other phone, which I'll turn on so we can stream from that if all things go well. Okay. Right, so you can see there we've got a few access points defined. We've got the developer days Wi-Fi. We've got some GPRS access points, but I don't actually have a SIM card in this device, so they wouldn't work even if I selected one. And then we've got the hotspot, so we'll choose that one. So that's going to stream data from my 3G connection here. Yeah, that's not on the wireless, via a wireless hotspot onto the Symbian device. So if I select that one and press play, then you can see it goes into the loading state. Cross fingers. And it's gone green, indicating that the access point is now active. And then at the bottom there, we've got, okay, it's telling us we're using Gareth hotspot, and you can hear that we've got data coming over the network. So this just shows how you can use the C++ APIs in QtMobility Bearer module together with QtMultimediaKit to control which access point is being used. Let's just see if I can, instead of using that one, if I can switch to the Qt Developer Days access point. See if it will use this one instead. It's gone green, which is a good sign. Okay, so now we're using the Qt DevDays access point. So that's all been controlled through Qt, no use of native platform dialogues, etc. It's a little bit stuttery. Someone's watching Nokia World, maybe. Okay. Okay, so that's the end of that demo. So the third topic I wanted to cover is around memory management and monitoring of memory usage. So this is really mostly specific to Symbian, for the reason that the Symbian devices, the Symbian 3 devices which are out there on the market today, so the Nokia C7, for example, which is the one that we've got hooked up here, N8, E6, X6, have a graphics and video coprocessor which has its own graphics memory, and it's a limited amount of graphics memory, so 32 megabytes. And that graphics memory is shared by the graphics subsystem, so OpenGLES and OpenVG use that, and the multimedia subsystem. So that's the pool from which buffers for video and camera are allocated. So if you combine use cases which make heavy use of graphics, so storing large pix maps, uploading large textures to the GPU, with multimedia use cases, so playing high-resolution video clips or starting the viewfinder, which takes a lot of memory, you can quickly exhaust that pool of graphics memory. And the likely result is that there's a graphics memory monitor on the platform which will kill your application. So as a developer, you'll just see your application start up, you'll do something, and it will die. And it's very difficult to understand why that happened. The good news there, before we get on to things that you can do about that, is that the next generation of Symbian 3 devices, such as the C701, have a lot more graphics memory. They've got a faster GPU and also more memory, so this problem is less likely to occur. So what can you do about this? Well, probably the first thing you want to do is understand how much memory is being used at any given time. And there's an API to do that, but it's not a Qt API. It's an EGL extension, the name of which is up there. This allows you to query the amount of graphics memory on the device, how much is being used in total, and also how much is being used by the current process, although for a reason I'll talk about in a minute, that last one is not very useful. Being an EGL extension, the API is not particularly friendly if you're used to Qt APIs, so I've written a wrapper around it, which is a Qt API, which is shown there at the bottom. So it's a Q object with a few properties on it and associated signals, which tell you when those values have changed. So this means that you can easily query the amount of memory that's being used, either from C++ or from QML, and understand what your application is doing. So I've got an example which shows that, which I'll just talk through this slide and then I'll go to the phone. So it's a QML application with a little bit of C++ to interface with that EGL extension. And what it does is it plays a video using the QML, QQuick video element, and then it shows on the right-hand side the amount of memory that's being used. So you can see there in that screenshot, I was running that on a C701, so total memory of 128, out of which I was using 49 megabytes, so plenty of headroom. But you'll see in a minute on the C7, you get a lot closer to exhausting the memory. But I should just point out that the middle figure there is the amount of memory that's being used by the current process, but it's actually a bit misleading because it only shows the amount of memory that's being used by EGL. It doesn't include multimedia use cases. So it looks like the current process is using very little there, but actually it's using a lot more than that because it's got a video surface allocated. It's just not included in that sum for some reason. Okay, so I'll just show you a demo of that. You just go to the phone. Right, okay, so here you can see we're on a C7, so 32 megabytes of memory. We're using 16 in total, mostly by the Windows server, which has cached various textures and pixmaps, VG images. And we haven't got a video clip loaded at this time. But if I just press the load button, so this calls video source equals, then you will see that number go down and then up. So the reason it goes down is because playing video on the C7 actually causes us to switch automatically from the OpenVG graphic system, which is the default, to the raster graphic system for reasons that I won't go into. So initially the amount of memory goes down because we free up an EGL surface, and then we allocate a video surface, and then it goes way up. So you can see there that we've got 25 megabytes being used, and that number should stay pretty constant when we start playing it. That's actually gone full screen. Okay, yeah, I forgot about that. When we're on when we've got a TV cable plugged in, it automatically routes video to full screen, so you actually couldn't see. If you did this on a device that wasn't plugged in, you'd see video in that thumbnail-sized window rather than going full screen. But the point still stands that API allows you to see how much memory is being used. Okay, so the other use case which tends to eat up memory is using the camera. Some of that is because we have to allocate buffers to capture the viewfinder data into. But as well as that, there are modules from the image signal processor firmware which also get loaded into graphics memory, which do things like image processing and stuff to do with the autofocus handling and that kind of thing, which eat up more memory. And also, there's no virtual memory on the GPU, so it's even worse because you fragment it very heavily. So one thing that you can do if you're using the viewfinder is you can avoid loading some of those modules by telling Qt that you're going to capture video rather than an image. So here we're looking at a use case where we just want the viewfinder for some reason. We don't want to actually capture anything from it. In that case, we can reduce the amount of memory that we're going to use by configuring the camera in video mode rather than image mode. If you need to capture a still image, then there's nothing you can do about it. You're going to allocate the full amount of memory. And you can also lower the viewfinder resolution. Although I think there's something has changed in the back end, which I wasn't aware of, that means that actually calling this API at the bottom here, set resolution, actually doesn't have any effect on the amount of memory that's consumed. So that may be a bit of a red herring. But certainly setting the capture mode to video does reduce the amount that's used up. I hope I'm not going to run into the same problem with this going full screen. But let's see. Okay, so here we have the camera is unloaded, as it says at the top of the screen, and we're using 19 megabytes, which, as I said before, is mostly consumed by the Windows Server process, not by this application. So if I start the camera and leave the Use Video Mode button unchecked, you should see that number jump up. Okay, so almost all of the GPU memory is being consumed. So if you want to do anything GLES related, then you're likely to run out of memory very quickly. Or if you've already got textures uploaded, then the application may just get killed. So if we stop the camera, it should go back down again. And this time, if we start the camera with video capture mode checked, then, okay, 25 megabytes. So I think we were using 29 a minute ago, so we've freed up about 5 megabytes of headroom of graphics memory just by using the video mode instead of the image capture mode. OK, so that's just another tip, which that was a graceful exit, which you can use to reduce the amount of memory that you consume. OK, so the final thing that I want to talk about is my favorite bit. So this is stuff that I've been working on recently, and this is what the advanced use cases which QtMultimediaKit enables beyond just creating a rectangle on the screen and putting some video or viewfinder data there. What else might you want to do? Well, one thing that you might want to do is you may want to process the video data in some way before it hits the screen. There's a lot of text on this slide, but really the point that I want to make here is that there's an API in C++ called QGL shader program, which is a wrapper around OpenGLES or OpenGL shader programs. And there's a QML binding to that called shader effect item, which was introduced in Qt 4.7.4. And especially the latter makes it really easy to add shader effects to your application. So if you're not familiar with shader effects, they are a part of the OpenGLES 2 or OpenGL 2 spec. And they allow you to define short programs using a C-like language called GLSL, GL shader language, which can either modify the vertices in the mesh in the 3D object which you're displaying, or modify the colors of individual pixels. And so the example that we're showing there is showing embedding a chunk of GLSL in QML via the shader effect item. So we've got a QML element there at the top, shader effect item, curly brackets, some properties, all of which should be fairly familiar, or at least syntactically fairly familiar to you. And then there's this fragment shader property, which is a string, and then there's this big blob of blue text. So don't worry too much about the details of that syntax if you're not familiar with GLSL, but that's a fragment shader program. Actually, yeah, a BF to anyone that can name what that fragment shader does in the 2 seconds before I switch to the next slide, he says quickly. OK, so the fact that we can embed GLSL in QML makes it really easy to use shader effects. You don't have to worry about creating OpenGL context and surfaces and connecting properties up to your application, passing in variables into your GL shader program. All of that is made possible for you by the shader effect item element. So just one thing to point out on this slide, that you can see there's a property there called granularity in the QML code. And then at the top of the fragment shader, there's a uniform called also granularity. And the fact that those two have the same name means that shader effect item connects the two up for you automatically. And so you can then tweak properties in QML, which then get passed into GLSL and can be used by your shader, which I'll show in a minute. Right, so I'll just switch devices. The reason I'm switching devices, so this uses, in Symbian, this uses a feature in the platform which is not in currently released versions of Symbian. It's coming down the pipe, but it's not there today. But this does work out of the box on the N9, on Harmattan. And so what this application does is it displays either video or viewfinder using the QML video or camera elements. And then it uses shader effect item to define an effect which is applied to that video. So I think it's probably better if I just show this running live. That one. OK, so first of all, this is just showing a static image. And as it says there, on the left-hand side, we can switch the source of the video data. On the right-hand side, we can switch effects. Also, we're showing on the bottom right the amount of video memory that's being used. It's not particularly interesting for this demo, but probably of more interest is the frame rate. So on the left-hand, bottom left corner, there's the frame rate. So the bottom, get this right, the bottom number is the average QML repainting rate. So it's averaged every second over a 1 second window. And the upper number is the instantaneous one. So that when I start the camera, you'll probably see the instantaneous one jumping around a bit more because frames don't arrive at an exactly even rate. But the bottom number will tell you the average one. So if I just start the camera. OK, there's you. And you can select some effects. So that's showing an effect in real time being applied to the viewfinder data. So that's a combination of an edge detection algorithm and some coloring, so that where we have edges, we apply some nice rainbow colors. So you can see there, the QML viewport is being repainted at about 30 frames a second. The camera is repainting, we're getting frames from the camera at only about 12 frames a second as compared to about 25, and we don't apply an effect. So there's a bit of a performance hit, but hopefully you'll agree it's quite nice. So there are other effects there, and as you can see, if I can grab hold of this little slidey thing at the bottom, oops, which I can't. Oh, there we go. Okay, so that's a parameter which my slider is changing in QML, and then that parameter is being mapped to a uniform in the GL shader program, which is changing the size of those little blobs in the billboard effect. We can do other nice things as well. So we can use time-varying effects. So we've got a number animation in QML, which is just changing some property, which then gets mapped onto the radius property of a ripple that we're applying. By the way, I guess you probably guessed it already, but left of the line is being transformed and right of the line is passed through, just so you can sort of compare the effect. What else can we do? We can, there's a pixelation effect there, which again, that by the way was the shader program fragment I showed earlier on. I really need to make this little control a bit bigger so I can get hold of it. So that's just changing the granularity of the pixelation. And another one that I quite like is a page curl effect, which is just a fragment shader. There's no vertex shader code in here. So in real time, that's causing the page to rotate, to curl up. And as you can see there on the back side of the page, we've actually got sort of semi-transparent monochrome version of the viewfinder. So you can sort of see through the tissue of the page. What else is good? Oh yeah, okay, so this is again a combination of an edge detection with some quantization of the colors to create a kind of toon effect. It's kind of like that film with Keanu Reeves, I can't remember the name of it, Through a Glass Darkly, if you've seen that. And there's a few more there. So this code is in the, that's the edge detection one, that's quite nice. This code is in the QML, in the repository that I published, which the URL is in the slides, so you can play with that. And you can also, as well as feeding viewfinder data into this, you can feed video data. So this basically causes us to destroy the QML camera element, create a video element. Oops, that wasn't what I wanted to do at all. That's actually, bear with me a second. That was the one I wanted. Okay, so this is actually a video from the Blender Foundation called Elephant Stream. So this is published under Creative Commons. And again, you can apply the same kinds of effects in real time. And you can see there that we're still, in the top left, we're still getting frames at 24 frames a second, which is the native frame rate of the video. So fairly good performance. Okay, enough playing with that. Okay, so it's a nice party trick. It's a nice effect, but maybe it could also be used for transition effects and fading in videos as they start to play, or applying some sort of more sophisticated post-processing, like camera aging, sort of hipstamatic style effects. Okay, so the last thing that I want to talk about is video and 3D. So again, once we've got video frames in the form of a GL texture, so as you've just seen, we can feed those to a shader and we can do cool effects with them. We can also feed them to a 3D scene. So Qt3D, as you'll know if you saw Sarah's or Danny's talks earlier on, is a very nice set of APIs in C++ and QML which allow you to create 3D scene graphs. And it comes with all kinds of nice things such as ability to import models, ability to create stock 3D effects such as cubes and teapots, ability to apply different types of materials to them such as textures. So with regard to that last point, so there's an API called Material in Qt3D, which is basically an abstraction around a texture or a flat color, which you can apply to one of your 3D objects. So you can load in a static image and you can apply that as a texture. But it doesn't, at the moment, abstract live textures, so textures where the content changes on each frame, such as video or viewfinder. But we can add that support with a little bit of C++. So in this example, what I've done is write some C++ which acts as glue between QtMultimediaKit and Qt3D. So there's an API in QtMultimediaKit called QAbstractVideoSurface, and that allows you as an application programmer to get individual frames piped through from the video decoder or from the camera viewfinder. And you'll get a handle to those video frames. The type of that handle varies depending on the platform, but on a mobile device, it's likely to be a GLES texture handle. And then this glue code that I wrote basically takes each of those texture handles and applies it to a GL material, which is being used by Qt3D to texture a 3D object. So that C++ code is exposed to QML via two new elements that I wrote. So whereas we've got the video element in vanilla QtMultimediaKit, there's now the video texture element, which has basically the same API. But instead of rendering to the screen, it renders to a stream of textures. And then there's this texture stream element, which allows you to make the connection between that texture source and your 3D object, which in this case is a cube. So let's go back to the phone. So same kind of UI as before. If we just select one of the stock objects, we can see that the static image is mapped onto it, so that's what Qt3D gives you out of the box. If you start the camera, and you get live camera viewfinder frames. It's a bit flickery. The integration between the multimedia stack and the Qt3D stack is not perfect, so there's a bug that I need to go and hunt down after this. But actually this, which I can show to people afterwards if you're interested, this actually works on MeeGo Hammer, and the performance is a lot better. The frame rate is better, there's no flicker, although it doesn't, for some reason, it doesn't work on all shapes. I don't know why that is, so again, there are bugs there which need to be tracked down, but just to let you know it does work, so we can map onto a sphere, kind of fisheye effect. This control here should, I wish this cable was a bit longer and then I could lift it up a bit more. This would, let's do that. Okay, so yeah, kind of a fisheye effect on the sphere. And a 3D demo would not be complete without mapping onto a teapot. And we can also map onto multiple items, so we can create a series of different Qt Quick 3D elements, and then make that same connection using the video texture element that I discussed a minute ago between our camera input and each of those elements. In this case, the frame rate's dropped down a bit, but we're still getting 10 frames a second, which is not too horrendous. And we should, again, be able to map a video onto the same thing.
Everything
Okay.
is safe,
There we go.
perfectly safe. Emo? Emo.
I think I need to put a volume control on this now. Okay, so go back to the slides. So that's basically what I wanted to cover. So just to summarize, I talked at the beginning about how you can get low latency response from QtMultimediaKit by pre-buffering and by reducing buffer size. And then talked about how you can programmatically control which access point gets used for streaming. And then talked about some Symbian-specific stuff around how you can monitor and reduce the amount of graphics memory that gets used. And then showed some cool stuff to do with advanced video rendering. So thanks for listening, and any questions? And by the way, if you do have a question, if you could wait for the mic before. Sorry, there's a gentleman at the back there. Go ahead.
Hi, nice
Hi.
presentation.
Thanks.
Just a technical question. How do you calculate the frames per second?
So we basically just hook into, for the QML painting rate, we hook into the paint event. So we add what's it called, an event filter on the QML viewport, listen for paint event, and then every time we get one, we increment a counter. And then every second, we look at how many frames were rendered that second and calculate a rate.
So if not the whole node tree is updated, then you don't update the whole screen. So it's not actually frames per second, right?
So there's two different counters there. So there's the QML viewport frames per second, So every time anything in the scene changes, the whole viewport gets repainted because it's OpenGLES. So that gives us the frame rate for the whole view. And then the counter in the top left was the number of frames we're getting from the video source per second. So we might be only getting 10 frames of video data per second and then rendering each frame 2 or 3 times as we animate the QML scene.
Okay. Thanks.
Okay.
Yeah, hi, nice presentation, by the way. So is there any other way to access the raw viewfinder data other than the abstract video surface thing?
No. In QtMultimediaKit, no, that is the API for accessing it. I guess the one thing you could do, well, actually that's not quite true. So in the shader effect item demo, we are not using QAbstract video surface. We're just rendering the video to a QML video element or QML camera element. And then the shader effect item implementation uses something called QGraphics effect, which is part of Qt GUI, which basically redirects the painting of the QML viewport. So instead of painting directly to a window surface, we paint to a frame buffer object. And then it grabs a texture, the backing texture from that FBO, and feeds that to the shader. So that's the other way that you can get access to the data. But either of those requires that you're using OpenGL graphics system. OK, thanks, everyone.